تهیه کننده دکتر نیما مهدیان. سعی می‌کنم با خلاقیت این شکل‌های قشنگ رو براتون توضیح بدم. راستی اسلایدها رو دونه به دونه تدریس می‌کنم و چیزی رو از قلم نمیندازم. Hello everyone and a very warm welcome to our masterclass explainer on the foundations of industrial automation. I am absolutely thrilled to have all of you international engineering students here today. In this lecture, we're going to learn how modern factories actually work. We're going to travel from the basic, high-level ideas all the way down to real-world engineering. So grab your notebooks and let's get started.
Okay, here's our roadmap for today's class. We'll start with universal automation, then move into an oil refinery case study. After that, we'll cover the three pillars: safe operation, production, and quality. And finally, we'll wrap up with a review and a quick quiz.
All right, let's dive into Section 1, Introduction to Universal Automation.
Now, take a look at the three examples we have here. Over on the left, we have aerospace engineering, which means guiding a rocket. In the middle, there's chemical processing with all those large tanks and pipes. And on the right, food and beverage manufacturing, like a bottling plant filling drinks on a moving conveyor belt. Now, they look completely different, right? But I want you to look at the blue lines connecting them. The control logic, the invisible brain analyzing data and optimizing variables, is actually exactly the same. It's the invisible architecture of modern industry. Whether you're programming a programmable logic controller, which we call a PLC for short, for a simple traffic light, or for a complex robot arm, you are using the exact same foundational logic.
Before we go any further, we need to define a very important word in engineering: process. What actually is an industrial process? Well, it's simply a transformation. You take raw inputs, you apply energy to them, and you get a high-value output. It's kind of like baking a cake at home. Your raw inputs are the flour and the eggs, your energy is the heat coming from your oven, and the high-value output? That's the delicious cake. In engineering, we just do this exact same thing, but on a massive scale.
Let's visualize that definition. Notice the arrows pointing around this diagram. Over on the left side, raw materials and input energy go into that white box. That box is our process. Then, over on the right side, our final products come out. But look closely at that red arrow on the bottom right: expelled or waste energy. This is a crucial engineering reality you need to remember. You never ever use 100% of your energy perfectly. There is always some waste heat. Managing that waste is a huge part of our job as automation engineers. Moving on to Section 2, the oil refinery case study. Let's see this in action.
So we just talked about that simple block diagram, right? But when you open up that black box, you realize an industrial process is never just one simple action. It's a highly complex combination of individual mechanical parts, things like pipes, valves, and heat exchangers, and they all have to work in perfect unison. As control engineers, we don't just look at the outside of the box. We actually have to control every single pipe and valve hidden inside of it.
Let's break down this oil refinery step by step, starting with Phase 1. On the left side, raw material, which in this case is crude oil, is stored in those large tanks. The blue pipes and pumps mechanically pressurize the oil, pushing it forward constantly. Then it enters the furnace. This is where we add massive amounts of thermal energy, or heat. We have to heat the crude oil to its exact boiling point. If the sensors right here fail, the oil won't be hot enough for the very next step, and the whole process stops working. And this brilliantly illustrates what happens next in Phase 2, distillation. The hot, preheated crude oil enters that very tall tower. Now, because it's so hot, it naturally separates into different products based strictly on their boiling points. The lightest vapor floats all the way to the top and becomes light gasoline. In the middle section, we get gas oil, and at the very bottom, the heaviest liquid just stays there as heavy residue. You see, the physics does the actual separation, but our control system manages the environment to make that physics possible.
Now, I really want you to focus on the red and blue arrows here. At the furnace, we inject massive amounts of heat. Those are the red arrows. But all the way at the top of the tower, at the condenser, we must use cooling, the blue arrows, to extract heat. Managing the raw material is honestly only half the equation. Controlling the thermal dynamics, meaning perfectly balancing the heat going in with the heat coming out, well, that is the core physical challenge of all industrial automation.
Let's pause for a quick second. I have a question for you all. Why do you think extracting heat, or cooling, is just as critical as injecting heat in a factory? Take a moment to think about it. Well, if you don't remove the heat, that energy just builds up endlessly. The temperature will rise and rise and rise until the entire system completely fails, or even worse, explodes. Cooling is exactly how we maintain control and stability.
Now for Section 3, the three pillars. Let's establish the rules.
I want you to think of running a plant a lot like driving a car. When you drive, you absolutely have to balance three things. First, you have to drive safely so you don't crash. Second, you have to drive fast enough to reach your destination on time. In a factory, that's your production rate. And third, you want a smooth, comfortable ride. That represents your product quality. A good automation system has to balance all three of these pillars simultaneously. But notice how pillar 1 is the large base that literally holds everything else up.
Let's look closer at that basin section. 4. Safe operation.
Notice the pressure gauge pointing right into the red danger zone and the digital thermometer showing an active alarm. Equipment has absolute metallurgical limits. So what does that mean in simple English? It just means the metal of the pipes can only handle a certain amount of pressure or heat before it physically breaks. Our control system is the primary safeguard here. Before a human operator can even react, the PLC program will automatically shut a valve or stop a pump to prevent a catastrophic physical failure. Safety is completely non-negotiable.
I want to quickly highlight a very common mistake students make. A lot of people think, oh, automation just makes machines run by themselves so human workers can relax. That is a massive misconception. The reality is that automation is a highly intelligent, real-time balancing act. Its real job is to safely manage incredibly dangerous physical forces at speeds and accuracies that a human operator simply could never achieve. Let's move to Section 5, Production and Quality. This is the business side of engineering.
Notice the graph we have here. That blue line represents external market demand, basically how much product the customers actually want to buy. As the demand goes up, our factory's production rate must also go up. The control system actively throttles, which means it adjusts, the raw materials entering the plant. It speeds up the pumps and conveyors to make sure the final output perfectly hits the exact target dictated by the business.
Now, what's really interesting about this slide is the consequence of bad control. Look at the funnel. The output must strictly fit within acceptable chemical specifications. If the automation system is unstable, you produce off-spec product, which just means bad product. And what happens then? You have to throw it away, just like you see in the waste pile at the bottom there. This destroys thermal efficiency because you wasted all that energy making garbage, and it totally destroys business profitability. In industry, quality is economic survival.
All right, we've made it to Section 6, final review and quiz. Let's bring it all together.
This table right here is an excellent summary to study. Our three main drivers are safety, rate, and quality. For safety, our target is to stay within physical limits. If we fail, we get catastrophic structural failure. For rate, our target is to match market demand. If we fail, we end up with a supply chain shortage. And for quality, our target is to minimize variance and eliminate waste. If we fail there, profitability completely collapses. Professional engineers use this matrix every single day in the real world.
Pay very close attention to this next part because it is a very common exam question. In process control, variables never exist in isolation. Notice the diagram. If you change the furnace temperature, you immediately impact the safety thresholds, the overall production volume, and the boiling point quality. You literally cannot change one single thing without affecting all the others. That deep interconnectivity is exactly why we need such complex mathematical logic programmed into our PLCs.
To conclude our core lesson today, let's pull all these key elements together. Industrial automation is not just turning machines on and off. It is the intelligent, real-time orchestration of complex physical assets, like our massive oil refinery, to guarantee structural safety, satisfy market demand, and maximize economic quality. It's a truly beautiful combination of physics, mathematics, and programming.
And with that, we have reached the end of today's lecture. For your upcoming exam, make sure you review the universal process model, the critical function of heating and cooling, the three pillars, the concept of metallurgical limits, and the interconnectivity of variables. Now, for your homework case study, I want you to think about a robotic assembly line making car doors. How do safety, rate, and quality apply there? What happens if the robot moves just a little too fast? Discuss this in your study groups, and we will talk about it first thing next week. Thank you all so much for your focus today, and keep learning.